All right, welcome. So here we are in section 11.5. We're talking about alternating series and absolute convergence, two very important topics. The absolute convergence maybe even more than the alternating series, but so be it. Both of them are very valuable. Let's take it one bite at a time. So when we have an alternating series, it's an alternating series is a series whose terms are alternating, right? Positive, negative, positive, negative. I assume that's what these drop boxes would give you. It's a series whose terms are alternating, positive, negative, positive, negative. Right. Under what conditions does an alternating series converge? Well, an alternating series of the sum ANs, which is equal to this, where Bn is just the absolute value of the ANs, would converge if the BNs are decreasing, which is what this is saying, and the BNs limit to 0. It's that simple. Alternating series are lovely because you have positive and negative terms. There's a cancelative effect there, and that cancelative effect makes the computations quite nice. If these conditions are satisfied, what can you say about the remainder after n terms? Oh yeah, the error is less than b to the n minus 1, which is actually kind of nice. So if you approximate the sum by the sum of the first n things, then the sum is going to be in error less than the next subsequent term. And if you draw yourself a picture, you can convince yourself of that. There's a picture in the text for this idea. Test this series for convergence or divergence. Well, hey, check it out. The terms here are alternating. The terms are getting smaller. 6/7 is bigger than 6/9 is bigger than 6/11, and those terms are going to 0. That checks all the boxes, right? If we're alternating, the terms are decreasing, and the terms are going to 0. That is convergent. So the alternating series test is lovely in the sense that it is maybe the most straightforward collection of criteria to check. It's visually accessible, doesn't require much limiting. You can kind of see the terms getting small and going to 0, and life is good. What about this guy? Hey, similar story, right? The factor of minus 1 to the n is giving us the alternating behavior, and that 3 to the n is giving us the decreasing, converging to 0 behavior that the alternating series test demands. So we would get convergence here. The bn's go to 0. The bn's here, by the way, what they mean by identify the bn is just pluck off the power of minus 1. Take the absolute value of the terms here. The minus 1 becomes just 1, and then you have 1 over 2 to the n, 1 over 2 plus 3 to the n. That limits to 0, and there's a decreasing behavior there, which means you would get convergence. This is actually a good question because it takes you through the whole process of an alternating series test, which is what WebAssign should be doing in other examples that it kind of sucks at. Okay, anyways, test this series for convergence or divergence. Well, we've got an alternating series because we've got the minus 1 to the n, but hey, check it out, that e to the minus n is going to go downstairs as e to the n, and as n increases, that denominator is getting bigger and bigger. Those values are getting smaller and smaller because we are alternating, because our terms are decreasing and tending to 0, we will converge. This is necessarily a feature of alternating series only. If we think that non-alternating series, as the terms get small, converge, we would be thinking falsely. Think of the harmonic series as that classic example. However, in the case of alternating series, life is about as straightforward as you could ever hope. Do the terms get small? Do the terms go to 0? Are the terms alternating? Maybe I can ask the alternating question first so that you can even ask the other two questions. So is it alternating? Do the terms get small? Do they go to 0? And if yes to all, convergence, it's no more complicated than that. Right, what about this? Now here, you got to think about what's happening as n's getting big. We're getting closer and closer to sign of 0. Moreover, the sign of a positive thing is positive because we're in quadrant 1, and as n is greater than 1, 7 pi divided by 1 is positive. Well, initially it's sine of 7 pi, which could be negative, but very quickly after you get, past n equals 7, you're going to be in a situation where all these things are positive. And so maybe the first couple few are negative, but the first couple few are irrelevant. What's going to determine whether or not the series converges or diverges is the last infinitely many terms always. And so here, are we alternating? Yes, minus 1 to the n. Are the terms getting small? Yes. Sine 0 is 0. And yeah, are the terms going to 0? They are. Sine 0 is 0. And so, life is good. We've got convergence here. What does it mean for a series to be absolutely convergent? Right, it means that the series converges, and if you put absolute values in the terms, you still get convergence. So absolutely convergent means like doubly convergent. The original series converges and the absolute values converge. What does it mean to be conditionally convergent? That means you converge under the condition that you don't have absolute values. If you parked absolute values, the cancellable effect of the terms goes away and the terms swell to infinity. So in this case, the sum of the terms converge, but the sum of the absolute values would diverge. That is what it means to be conditionally convergent. What can we say about if the series of positive terms converges? What can you say about this? Well, hey, if the positive terms converge, then the alternating series must converge. Because the alternating series is going to have an easier time converging because the positive terms are just going to be, as you add them up, getting bigger and bigger and bigger and bigger. And if that doesn't go to infinity, then when you add and subtract every other term, there's no way that goes to infinity. And that's the idea here. So we would get absolutely convergent as a result. Right, but now here is a great example. You should be able to explain this in 2 or 3 sentences. If you can't explain this in 2 or 3 sentences, star it, come back to it, study it. Here is a great example. We have an alternating series. Downstairs, we have a power of n to the 6th sevenths. There's no doubt that as n gets big, the terms of this series get smaller in absolute value, and the terms go to 0. This series, as an alternating series, converges. However, if you put absolute values on each of the terms, that -1 goes away. And now you just have a p series, n to the 6 sevenths. And n to the 6 sevenths does not have a big enough power of p to converge. And so here is a classic example of a conditionally convergent series. The series that is alternating converges by the alternating series test. The series that is the absolute series, put absolute values on, the -1 at the end, put -1 goes away. Now you just have a p series, that thing diverges. Classic example, star it, know it, inside out. Okay, let's see, we're looking at this series here. Right, so looking at this series, if you follow the alternating series test, which is what this is trying to do, 1 over 7n plus 1, take the absolute value of the terms, the limit is 0, you're decreasing, so by the alternating series test you converge. However, if you take absolute values here, you will have something that limit compares to 1 over n. And as a result, will diverge as an absolute series. So the alternating series converges, but the absolute series doesn't. This is conditional convergence in the flesh. Here, now another one, star it. Make a note of it. Yes, the alternating series is occurring. You have the -1 to the n. Yes, the terms are getting smaller. As n gets big, the denominator is getting big, and the terms are getting small. And yes, those terms are going to 0. So by the alternating series test, we have convergence. And if you put absolute values on that thing, you get 1 over n to the 5th plus 3, which compares to 1 over n to the 5th, and 1 over the n to the 5th is a p series that converges. So the absolute series converges as well here, which means this is something that's absolutely convergent. Not only does the alternating series converge, but the absolute series converges as well. Great example. What about this one? Well, as the n gets big, the denominator gets big, the fractions go to 0, you get convergence by the alternating series test. But we've seen an example like this in the previous section, 11.4, where if you compare that to 1 over n, the ln function, by virtue of its concavity, concave down, is going to show you that the ln's are less, which means the 1 over ln's are greater, which means you diverge as the absolute series. Here's another classic example of a conditionally convergent series. I put 4 stars on this one. This is such a good example. Okay, right, if we converge as positive terms, then we necessarily converge as alternating terms. It is always easier for the alternating series to converge. It is harder for the positive series to converge. So if the positive series converges, then the alternating series must. It's that simple. Right, if the original series is divergent, then the absolute series is divergent. That is also true, because, is that true? I have to think about that for a second. Yeah, that's got to be true, right? Because if the original series is divergent, then there's no way the absolute series could converge, because the absolute series is always going to have a harder time converging than the original. So, yeah, this is, if the original is divergent, the absolute series must be. There's no in between. Alternating series always converge. No, no. You could imagine something like uh, 1 minus 0.01, 2 minus 0.01, 3 minus 0.01, plus 4 minus 0.01, plus 5 minus 0.01. It's alternating. Every other term is positive and negative, but those positive terms are getting enormous, and those negative terms are always negligibly tiny. And when you add up those numbers, that thing's growing without bounds. So alternating series do not always converge. It is often that they do when you see them on a quiz or a test, but that does not mean that they always do. Be conscientious of that. Another great true or false question. All right, that's a wrap on the WebAssign here. So let's call this a wrap on the WebAssign discussion up to 11.5.